right, welcome back everyone to the afternoon session. Welcome back everyone to the afternoon session. Our first speaker will be Claudiu Raicu, who's going to talk about cohomology of line bundles on flag varieties.
For the invitation, it's really an honor to be here. It's been a wonderful conference so far, and I've learned a lot of things. I'm gonna do my best not to ruin it. So just to start with a disclosure, I mostly do commutative algebra, really commutative linear algebra. So let me start with a linear algebra problem that hopefully we've all solved at some point. So K is going to usually be a field for me, mostly of positive characteristic. So I fix a non-negative integer D, I look at the set 1 through D, and I form a complex indexed by the subsets of this D element set, okay? And the differentials are defined by just removing one of the elements in the set with an appropriate sign. And hopefully you've seen this as a complex computing the reduced homology of the simplex. This give an example for D equals 3. And the exercise is to show in as many ways as possible that this complex is exact. Okay, so I hope everybody has done this at least once. Okay. So what I want to do is I want to change this complex a little bit by rescaling some of the entries. So here's one example of a rescaling that still gives me a complex. Of course, if you are over a field of characteristic 0, the homology is not going to change. So, but over a field with 2 elements, some of these entries are going to become 0. There's certainly going to be homology at the end. Yes, and the question is, how does the homology of this complex depend on the characteristic of the underlying field? Okay, so again, characteristic 0 or large will give you an exact complex, but for small characteristics, maybe something interesting happens. So let me explain my choice of rescaling. I'm sure there's other interesting ones. So to explain that, I'm gonna think of this D element set as just the labels of the edges on this chain. So for every subset of 1 to D, I just draw the corresponding labels, and then that gives me decomposition into a disjoint union of intervals. I'm going to compute the size of an interval by just counting the number of nodes it covers. And then when I remove an element in the set J, then that exactly will break down one interval into 2 pieces. Yes? And so the coefficient that I'm going to put when that happens is just going to be a binomial coefficient. So if I break up an interval of size W into one of size W prime and complement, then I'll write the binomial coefficient. Okay, that's how I got this complex on the top of the slide. So for instance, from the interval of size 3, over here, I remove the middle guy, breaks it up into 2 intervals of size 2, and I write 4 choose 2 with an appropriate sign. Okay. So here's the complex in more detail, right? So for instance, here I have an interval of size 3 that when I map down, breaks down into an interval of size 2 and an interval of size 1. I'm going to write 3 choose 1 there. Okay. If I'm here in the middle, there's these 2 intervals of size 2. If I map to this direction, one of them will break up into 2 intervals of size 1, and I write 2 choose 1 and so on. Okay. So that's how I'm going to construct a complex for every D. So I'm going to call this an arithmetic causal complex again in characteristic 0. This is really just the homology is going to be exactly the same as for the simplex that is going to be 0. Okay, and so the question is, how do we describe the homology of this in characteristic P? Has anybody seen this example before? Or do you have a guess for what the answer is? Okay, so, it's clear in most characteristics, exactly. So I'm mostly interesting characteristic 2, really, but anyways. So let's see how this works. So I want to give you an answer. So to give you an answer, I have to introduce the main players. So those are going to be the integers that are congruent to 0 or 1 mod p. So you should ignore every integer that doesn't satisfy that property. So of course, when p equals 2, these are all of them. But when p is equal to 3, so I listed here in this table the well, just all the integers, and then if I ignore the ones that are not 0 or 1 mod 2, then I can just enumerate them and assign them an index. So this would be the 0th, first number that's 0 or 1 mod 2. This would be the 2nd, 3rd, 4th, 5th, and so on. Yeah, so there's a formula to figure out the index. You do division with remainder, right? M as PA plus B, with B congruent, with B actually equal to 0 or 1. And then for the index, you just replace P by 2. So this is 2A plus B. So again, in characteristic 2, nothing happens, but in general, you get these funny numbers. So now, if I have a tuple of positive integers, each of which is congruent to 0 or 1 mod P, I can define the index of the tuple to be just the sum of the indices of the entries. And now for my positive integer D, I look at all the p-adic expansions, so all the ways of writing D as the sum of alpha I p to di. So these alphas can be digits that are larger than p. You don't have to be, yeah, so this is not unique. But what I want them is to be congruent to 0 or 1 mod p, okay? So if the integer itself is not 0 or 1 mod p, it's not possible to do this. So for D equals 8, you get the empty set. But for D equals 9 in characteristic 3, these are the 4 ways of writing it. So 9 is 3 squared, but it is also 3 times 3, but it is also 6 times 1 plus 1 times 3, and it is also just 9 times 1. If you look at all these entries, they're all 0 or 1 mod 3. It is true that 9 is also 3 times 1 plus 2 times 3. So you might think about the digits 3 and 2, but they're not 0 or 1 mod 3. 2 is not allowed. Okay, so this is all that's allowed. And then if I want to figure out the p index, I'm just going to have to read off this table. Yeah, so 1 has index 1, this is 0, so total sum of the indices is 1. 3 has index 2, 6 has index 4, plus 1 gives me this 5, and 9 has index 6. Okay, so that's how you assign this p index to every positive integer. Okay. And here's a theorem. The theorem says that if you look at the Poincare polynomial, the generating function for the homology of this complex, of this arithmetic causal complex, that is exactly given by a generating function parameterized by this p-adic decompositions of not D, but D plus 1, where the digits are 0 or 1 mod P. Okay, so hopefully there will be some sketch of this theorem, but the way we get to it with so Keller is in the audience and he can probably tell you a lot more about this theorem. The way we get about to prove this theorem is really by going through some cohomology calculation on a projective space. Namely, you take the cotangent sheaf, the sheaf of differentials on projective space, you apply the symmetric power functor, and you look at the cohomology groups of this sheaf. And it turns out to be, maybe because I'm doing cohomology as opposed to homology, I have to reverse this polynomial, but this is exactly this. There's one contribution to cohomology for each p-adic expansion with digit 0 or 1. Okay, and I wrote down some examples. So if D is equal to 0, that's a complex that's just one vector space, k in degree 0. Of course, the homology is one-dimensional. And the geometric counterpart of that is just that the cotangent sheaf has only one cohomology in degree 1. Okay. Now for D equals 1, if you look in characteristic 2, you'll get this polynomial 1 plus t, which is translates into the fact that the symmetric square of this cotangent sheaf has two cohomology groups in degree 1 and 2. And the last example is the one I had on the previous slide. So I have to do d equals 8 because I'm looking at p-adic expansions of d plus 1. And I had 9 on the previous board. And this is what the polynomial is. And again, it means something about cohomology if you want. Okay. So I'd like to at least give an indication about how this proof works. So there's these two objects, the arithmetic causal complex and this set of p-adic expressions for d plus 1, which perhaps are a priori unrelated. And the way we relate them is by going through this geometric object over here, right? So this is some, you can think of it as a complicated vector space. Maybe it's a family of vector spaces, and then there's a functor that associates to it some cohomology. So it's maybe not super important to do to understand that. So Jake, yes. That's a great question, and we can put it on the list of open problems. We haven't added now, but yes, I mean it's certainly something to. The question is, what if we add up all the symmetric powers and their cohomologies, and maybe put this in some generating series, and then the question is, what do we get? Yeah, and we haven't done it, but it would certainly be something interesting. Okay, so the point is to relate these two by this geometric object. And so I agree this is complicated. Maybe for some of you it's not, but to me it's complicated. So there's two ways of trying to approach this. I can approximate it from below, by which I mean there's some filtration of this object, and then I understand the composition factors, hopefully. Or I can approximate it from above. So I surject it onto by some simpler object. I take the kernel, the difference, and then I keep approximating that. That's what we call a resolution in commutative algebra. Okay, so there's two ways to approximate this object, and it turns out if you approximate it from above, you'll get something that is related to this arithmetic causal complex. If you approximate it from below, it's something to do with these p-adic expressions. Okay, so maybe I'll say a few more words. So what is the approximation from above? That is the resolution of this symmetric power. So here, again, I think it's perfectly okay if you think of omega as being a vector space, and omega I is just the exterior powers of that vector space. So the statement is that there is a way to write down a resolution of this symmetric power where the terms are just tensor products of exterior powers. Now think of those as somehow simpler objects. And that's my approximation from above. There's a whole literature about constructing this for more complicated functors than the symmetric powers, for sure modules. It started with Akin and Buchsbaum, and then Rota joined in, and there's still not a clear picture about how to do this for arbitrary sure modules, or explicitly enough so that we could do calculations. And then Totaro has a very nice little paper where basically this complex shows up in there. So he actually studies the cohomological dimension of polynomial functors of certain degrees, and this resolution plays an important role there. Okay. If you like symmetric polynomials, then you would know that exterior powers have to do with elementary symmetric polynomials. So if you take characters and take the Euler characteristic of this complex, you will get a way of expressing the fourth complete symmetric polynomial. That's just the Jacobi-Trudi identity. Yes. So I don't want to be controversial. I think maybe some people call this a categorification. I'm just going to call it a fun fact. Yes. So now it turns out that there's some mumbo jumbo with cohomology. If you apply a cohomology to this resolution, then you will get exactly the arithmetic causal complex. And then there's a hypercohomology spectral sequence that tells you that if you compute the homology of that arithmetic complex, that's the same as computing the cohomology of sim4 or of the symmetric powers of this cotangent sheaf. Okay, so this is approximating from above using these resolutions. Okay, so now there's another way to approach the cohomology of the symmetric powers by filtering with sub-objects. Yes. And to define them, I need to talk about this concept of truncated symmetric powers. So I'll get back to this filtration at the end of the slide. So in characteristic P, there's other functors besides the usual ones, symmetric powers, exterior, sure, that you can define using the Frobenius. So the Frobenius functor itself gives you a sub-representation of the Pth symmetric power, just the linear span of Pth powers. Yeah, so if you choose a basis, this is just the linear span of x1 to the p, x2 to the p, xn to the p. And now you can mod out by the ideal generated by the Frobenius. If you mod out the polynomial ring by that ideal, then you get a truncated symmetric algebra in degree d. The degree d component is what we're going to call the d-truncated symmetric power. Okay, so this is something that doesn't really exist. It exists as a symmetric function, certainly, but it's not representation in characteristic 0. Okay. And now the p-adic expansion. So if I have a tuple of integers alpha 0 up to alpha k, I take truncated symmetric alpha 0 power, and then truncated symmetric alpha 1 power, and I twist by the Frobenius, and then truncated symmetric alpha 2 power, I twist by Frobenius twice. I take the tensor product of these. Turns out it's an irreducible representation of a general linear group, and it's the natural building block for the symmetric power of V. Yeah, so Doughty has studied this long time ago, how to filter symmetric powers, and turns out that the composition factors are these F alpha V's for every p-adic expansion of D. And so now, of course, these are functors, you apply them to the cotangent sheaf. I'm not imposing I don't want the digits to be small. They can be arbitrarily large. So for every one of what you get one. No, for every D, there is a filtration where the composition factors are these F alphas, and they're parameterized by all the ways of writing D in base P. All of them. Yes. So the D gives you the symmetric power, and then the composition factors come from the p-adic expansions of that D. Yep. So there's no 0 or 1 yet. For which these are the composition factors, yes. Ah, that's a, yes, that's a composition factor, is not a, yes. Yeah. I mean, sometimes it's a good idea to use confusing notation so that you engage the audience. Because of course on purpose. Yes, there's more questions, yeah. So the question is if the omegas are quotients of? The maps. Yes, a lot of them are co-products, yes. I wrote this on the slide, but I didn't want to insist. So the point is you need to know the maps in cohomology that are induced by all this maps in the resolution. And so there's something to be checked to see that you get the arithmetic causal complex, but yeah, yes. It's a great question. So the question is, what order do the composition factors come in? And it's the right order so that you can prove that the connecting homomorphisms are 0. So that's why each one of the composition factors, as long as it has cohomology, it contributes. And I guess the last line of the slide is to the point that there will be cohomology exactly when the alphas are 0 or 1 mod P. And otherwise, there's no cohomology whatsoever. And if all the alphas are 0 or 1 mod P, in fact, the cohomology is 1 dimensional. Okay, and so that gives you the bijection between these composition factors that contribute to cohomology, and then the p-adic expansions where digits are 0, 1, 1. Okay. No. So this is completely independent. So these are two completely independent ways of looking at sim d plus 1. So one of them realizes the connection to the arithmetic causal complex, and I still don't know how to compute its cohomology at this point. But the other one realizes the connection with this filtration, and based on the filtration and on the fact that the connecting homomorphisms play nicely, I know how to compute cohomology. So basically, I know how to do things on this side because I know how to compute cohomology for composition factors. I know how to put the information together to get to sim d plus 1. And I know that it has this interpretation. Yes, and so that's why, yeah. That's right, yes. So you can think, so it's nothing to do with the maps here. The maps here I understand very well. But then I don't know how to do the linear algebra. Okay, so. All right, so I mean, my title was about cohomology of line bundles on flag varieties. It probably doesn't look like I've done anything. There's some cohomology, but there's no line bundles. Okay, so let me give you, so if you like that example, maybe now you will just enjoy a little bit of the general theory. So I want to just remind you about flag variety. So V is an n-dimensional vector space. I can form a variety that parameterizes complete flags of subspaces. So this is just increasing chains of subspaces, dimension 1, 2, up to n-1. There's variations where you look at partial flag varieties. So you skip some of these guys. Yes, you just look at subspaces with dimension in a given set J. And we all know our favorite examples. So these are Grassmannians when you only take one intermediate subspace, or projective spaces, dual projective spaces when this intermediate subset is just 1 or n-1. And there's another one that I like, which is called the incidence correspondence. So this parameterizes lines and hyperplanes containing them, but of course you can think of it as a partial flag variety 1 n-1. Yes. So there's lots of these nice geometric objects that you can construct from a vector space. And they come with vector bundles or line bundles on them, which are simply families of vector spaces parameterized by the space. Yeah, so I've drawn a picture of a line bundle over here. So it's a family of lines parameterized by this base space, which is maybe a P1. And the point is that there is a natural definition of all kinds of families of vector spaces associated to this flag variety. So for instance, as you vary the point in the flag variety, as you vary the flag, if you look at just the I-dimensional vector space, that gives you a family of I-dimensional vector spaces tautologically attached to the flag variety. Yes, you could do quotients, or you could do something like VI mod VI minus 1, which would be like a one-dimensional vector space that varies with the point in the flag variety. Yeah, so there's natural families of vector spaces you can attach to these flag varieties. And then one thing that you could ask when you have a family of lines like here, you could ask, is there a way to construct sections of the projection map? Is there a way to come up with a copy of this flag variety or of P1 that naturally lives inside the total space? And it turns out that these the set of sections have an additive structure. They're vector spaces. And then you look at functor of taking sections. It's not exact. You derive it. You get some higher cohomology functors. That anyway, there's some recipes that attach to these geometric objects finite dimensional vector spaces. If you come from the representation theory, you would say that the flag variety is a quotient of the SLN or GLN by a Borel, and then global sections means induction. These higher cohomology groups mean derived induction. Okay, so these cohomology groups of line bundles or tautological vector bundles on the flag varieties will come with a natural action by change of coordinates. there will be representations of the general or special linear group. And then, of course, you probably know that their structure is going to be a lot more subtle in characteristic P than it is in characteristic 0. Okay. So here's the wide open problem in this area is to, give you a line bundle on a flag variety, determine the cohomology groups. So for finite characteristics, so I was, of course, the theory in characteristic 0, we understand completely what happens is the Borel-Weil-Bott theorem, and I'll mention that later. But this is wide open in characteristic P. And so determine means different things to different people. To me, is I would like to at least be able to say, based on the answer, whether the groups are 0 or not. Yes. So ultimately, it's vanishing and non-vanishing theorems that I'm interested in. Okay. Okay, so let's start with the classification of line bundles. It turns out that these line bundles Li that I wrote down over here, they generate all the group of all line bundles on the flag variety. And there's a relation between them. If you tensor them together, you get 0 basically. So the group or the Picard group of the flag variety is just Z to the n modulo this diagonal 1, 1, 1, 1. Okay. So I'll simply write O of lambda for the line bundle corresponding to the tuple lambda. And there's a similar classification if you work on a partial flag variety. What's going to happen is that you're going to get fewer lambdas, namely some of the consecutive entries in the sequence lambda will have to be equal to each other if you look at the partial flag variety as opposed to the general. Okay, so studying partial flag variety is in some sense a sub-problem of the general flag variety case. Okay, so that's what I wrote here. If you have line bundles on the flag variety, there's always a on the partial flag variety. So like on projective space, there's always a corresponding line bundle on the full flag variety that has the same cohomology. But maybe more interesting is that if you take a line bundle of the full flag variety, there is a way to produce a vector bundle, a higher rank bundle on a partial flag variety that has the same cohomology. Not always, but often it's the case that you can do that. And here I wrote down one example. So projective space is a partial flag variety. There is a forgetful map like this. And if I look at a weight of the form minus d minus 1, d plus 1, and then all zeros, and I push that down to something on projective space, then I'm going to get exactly the symmetric powers of the cotangent sheet. What I'm saying is that there's the same cohomology. So you can interpret this theorem that I had with Keller about computing cohomology of sim d plus 1 of omega as just computing the cohomology of these types of line bundles, where the second entry is the negative of the first, and then the other ones are all 0. So you can take this in two ways, I guess. You can be completely unimpressed about our theorem then, because there's really not many weights that we can do something about. Or you could just, if you thought it wasn't straightforward, maybe you just get an appreciation of how difficult this problem will be if you want to solve it for an arbitrary lambda. Okay. All right. So we classified the line bundle. So it's a lattice of rank n minus 1. And I asked a question about vanishing and non-vanishing of cohomology. So let's start with H0. The question, when do these line bundles have sections? And that's completely understood. So it turns out that the line bundle has sections if and only if the corresponding lambda is a linear combination of these fundamental weights. And what that translates into, if you think about taking positive combinations of these weights, is the same as saying that the lambdas are non-increasing. Yeah, so that lambda is a dominant weight. And in that case, we also know that this set of global sections is naturally identified with a Schur functor as lambda of V. Okay, so that's independent from the characteristic. And there's a famous theorem of Kempf that was reproved later by Habush and Anderson. It says that for such dominant weights where you do get H0, every other cohomology has to vanish. So there can only be one cohomology group that's non-zero. And in fact, there is one here. Okay. So we know H0 very well. We know when it's 0, when it's not. We know what it is. And in characteristic 0, this phenomenon that there's always at most one cohomology that's non-zero persists. Okay, so assume that the field has characteristic 0, take any weight whatsoever. There's at most one cohomology group that's non-zero. It can happen that they're all 0, and there's a simple rule for when that happens. So lambda I minus I should be equal to lambda j minus j for some pair of indices. And in that case, you'll get all the cohomology to be 0. And otherwise, there will be at least one that's non-zero. And when it's non-zero, then the cohomology group itself is a sure functor. It's an irreducible representation of the special linear, general linear group. Okay, so we understand completely. I wanted to maybe do one more example. I like the symmetric powers of omega, so I guess I have to use them. So in characteristic 0, the claim is that the cohomology of symmetric powers of omega is identically 0. Okay. So of course, that's because it's the cohomology of the Koszul complex, and that's 0. Yes, so we know that already. How would we get it using Borel-Weil-Bott? Well, first of all, you have to believe me. I told you this, and just believe me that the cohomology of this symmetric power is the same as the cohomology of O of lambda for a certain weight lambda with n entries, namely minus d minus 1, and then d plus 1, and then zeros. Yes, so we've talked about this before. So why does Borel-Weil-Bott predict that this cohomology is 0? Well, if you look at the difference, lambda 1 minus 1, that's negative d minus 2. But that's also the same as lambda d plus 2 minus d plus 2. Yes. And I need to make sure I have at least d plus 2 entries to apply this theorem. And that requires d to be smaller than r. So this projective space needs to be large enough for this theorem to be true. It's easy to see that you get counterexamples immediately if you make the space small. Yes, if on P1, omega is just O of minus 2. This is a very negative O, certainly. Anyways, if you've seen this, you would immediately convince yourself that there's no way this statement would be true for small values of R. Okay, that's the theorem I had with Keller in the beginning in characteristic 0. Yes, it's equivalent to saying that the Koszul complex is exact. And yeah. All right. So I've drawn a picture here for Borel-Weil-Bott on a 3-dimensional vector space, again, characteristic 0. So there's this familiar chamber decomposition of the 2-dimensional weight lattice. This is the dominant chamber. It's spanned by omega 1 and omega 2, so this fundamental weight. Here, I'm going to see all the line bundles that have global sections. This area is all of the ones that have H1. And here, this is all of the ones that have H3. So the flag variety is 3-dimensional. If you know about Serre duality, then you would see the symmetries in this picture where H0 is exchanged with H3. This guy is exchanged with H2. So Serre duality is just the symmetry about the origin. And then there's also these blue lines. These blue lines cover certain weights, and those are the weights where all the cohomology vanishes. Those are the weights corresponding to the equality lambda I minus I equals lambda j minus j. Okay, so there's similar picture in higher dimensions. Characteristic 0, everything is completely understood. Okay, that's what we have. Okay, so I'm still telling you some of the story. So how about characteristic P? So probably Mumford was the first one who observed that you can have multiple cohomology groups that are non-zero. And this is really word of mouth. I think this is his example, -220, which is the sim2 of omega in characteristic 2 that I've talked about earlier. Yes. So I hope we can all prove this fact at this point, that there's 2 non-trivial cohomology groups. Okay. So then Anderson gave a complete characterizations of the weights where H1 is non-zero. And then once you know chem vanishing, and this the result of Anderson, you could apply Serre duality, and try to understand what happens with cohomology groups at the top. So the flag variety is dimension n choose 2, so you'll get a characterization for when these two cohomology groups are non-zero. And again, in the middle, the problem is wide open. Yes, so just understanding even the vanishing and non-vanishing in the middle is not understood. Okay, so the best results are for n equals 3. So Griffith was a student of Mumford. In his thesis, he characterized the vanishing and non-vanishing for cohomology on the three-dimensional flag variety. And okay, so that's problem prime, but you might want to understand what representations you're getting, or the characters of those representations, the symmetric polynomials that describe the cohomology. And Donkin gave a complicated recursive formula, again, for n equals 3. And Linyuan Liu, in her thesis just a few years ago, she gives a vastly simplified recursion. So now I think we have a clear understanding and a very quick way of determining the characters. Of course, it's recursive, but it's a nice recursion. Okay. So maybe there are a couple more results, but that's it. Okay. But that's it with. I still have that's it with the general theory. I have how many minutes I have? I mean, we can stop maybe if there's a treats. Okay, so there's lots of open problem here, open problems. So let me go back to this example I talked about with Keller. So symmetric powers of omega we understand very well. How about sure functors of omega? So can you describe them? So what we can show is that, again, as in the case of symmetric powers, there is no group action really on these cohomology groups. So this is these sure functors of omega are trivial representations of the symmetric group. So the representation theory is not part of the difficulty here. It's understanding these complexes and how to compute their cohomology. And so the question is, for these vector spaces that have no structure whatsoever, can you describe them? Yeah, can you understand how to compute them recursively? And so we can try to imitate the argument we have for symmetric powers, and we get some results for hook shapes or for two-column partitions, but we don't understand the general picture. And part of the problem is that this program by Akin and Buchsbaum, and then later on Rota, is not sufficiently developed. We do not have a good understanding of resolutions of sure functors by exterior powers or tensor products of exterior powers. And that's one approach. And then, of course, the other approach that we use is to break this down into composition factors. So that will be the problem of understanding how the composition factors for a sure functor in positive characteristic. So you need to understand the structure of sure functors in positive characteristic, and which is another very wide open question, at least for small primes. And certainly we can make progress using that approach. Yeah. Okay. So anyways, I said here that again, this calculation on projective space is equivalent to looking at weights for the complete flag variety that have this form. So mu1, mu2 up to mu r, that's a partition. And then you take the negative of the size of the partition as the first entry. Okay, so these are the kinds of weights that you can show the cohomology has no group structure. So it says, from the representation theory point of view, is as simple as possible. Yeah. So maybe it would be a good place to start. All right. So what else can you do? Is you identify these weights when there's no group structure. Another thing is maybe you look for a nice family of weights, perhaps coming from partial flag varieties, where you can make more progress. Yes. So we certainly know the cohomology coming from projective space for Grassmannians. So these Picard rank 1 cases. So the first interesting case is to look at some two-dimensional lattice inside the weight lattice, and then ask, can you prove any results in that case? Okay. And so I told you I like the incidence correspondence of this family of lines and hyperplanes, yeah, that are incident. And with my student Zhao Gao, we actually were able to characterize the vanishing and non-vanishing of cohomology in every characteristic. So writing down the exact result is probably not great, but looking at this picture might be a little better. So looking at the line bundles on the incidence correspondence has to do with looking at the slice inside the weight lattice, which is spanned by the first and last fundamental weight. So just looking at linear combinations of omega-1 and omega-n minus 1. So it's two-dimensional, looks a lot like the SL3 case, but I'm allowing the vector space to be arbitrary dimension. If you ignore this red region, Borel-Weil-Bott will tell you we only get H0 here, only Hn minus 2 here, only Hn minus 1 here, and so on. Yes. And so what we prove is that when you pass to characteristic P, you get this extra cohomology throughout the red region. Yes, and this red region has some kind of a fractal behavior. Of course, there's explicit formulas we can write down, but there's a lot of symmetry to this picture coming from the fact that you still have Serre duality. You can interchange lines with hyperplanes. So really, if you understand what happens in one of these regions, then you understand what happens everywhere. Yes. Here, I mean, one of the red regions, right? Here, this is Kemp vanishing. H2n minus 3, it's Serre duality and Kemp vanishing. So really, this region is the interesting one. And it turns out that if you just look within this region, then computing cohomology again translates into a problem on projective space. So this is no longer symmetric powers, but it's divided powers of the cotangent shift plus twists. You have to have two degrees of freedom. You can take arbitrary divided powers, and then you can twist by O of 1. Yes. And anyways, it's elementary to prove that you get non-vanishing in these regions. And then what we need to do is we need to prove a vanishing theorem. And then there's a lot of commutative algebra there. It's still breaking down the divided powers and then controlling the composition factors and the so-called Castelnuovo for regularity, which I don't think I should define here. Yes. Yes, so that's a great question. It depends on P in several ways. So here I draw the picture for P equals 3. So you get groups of P minus 1 triangles that grow in size exponentially with P. Yeah, so P equals 3, this is these two, and then there's another 2, and then another 2 that get bigger and bigger with the power of P. So it highly depends on the prime number, yes? But of course, the natural question is, what happens below this red region? What's the structure of the cohomology? How big? I mean, it's non-zero, but how big is it? Yes, can we describe the underlying symmetric polynomials? Yes? And that we don't quite know how to do. We know to do it in a few cases, but not in general. And so perhaps, I mean, this again, it's going to lead to a conjectural situation, but I want to indicate what building blocks seem to be contributing to this cohomology, to this red regions, okay? So this has to do with symmetric polynomials, yeah? So remember that, so I'm going to write, bracket M for the character of a module M. So the character of a symmetric power is just the complete symmetric polynomial. The character of the Schur functor is just the Schur polynomial. And then there's truncated versions of this, yeah? So if you look in the truncated symmetric algebra in degree D, this is a nice symmetric polynomial. It's the sum of monomials where no exponent is D or higher, yes? And you can then define a new symmetric polynomial, this truncated Schur polynomial, by using Jacobi-Trudi and replacing the complete symmetric polynomials with these truncated ones, okay? Well, what's going to happen is that typically this is not going to be the character of a representation. So it's only an actual representation. It's only going to be virtual. And but anyways, it's a symmetric polynomial. So there's a lot of questions about understanding how to write these truncated Schur polynomials in terms of characters of simple modules. And again, that has to do with a whole other interesting area of modular representation theory. So what we observe is that these truncated Schur polynomials seem to be the building blocks for the additional cohomology groups that you see in characteristic P. So I switched to a P equals 2 example because it's a little harder to draw for P equals 3. So here P equals 2 means you see a triangle and then it scales by 2 and then by another 2 and so on. And but what I'm saying is that these red regions, if you look more carefully, they decompose into layers. So these red dots, their cohomology group, their contributions to cohomology that have to do with P truncations of Schur functors. The green ones have to do with P squared truncations of Schur functors. And then the yellow ones with P cubed truncations. There are all these kinds of truncations you can define for powers of P, not just for P itself. And I know that my drawing seems to make them all look the same, but they're not. It's just the underlying building block is always the same, but then it comes with a multiplicity. You have to always tensor by a more and more complicated symmetric polynomial. And turns out that for P equals 2, the right symmetric polynomial is what I call the Nim symmetric polynomial. It indexes winning positions in the game of Nim. Does anybody know what the analog for P equals 3 is? We would very much like to know what's a game of Nim that has to do with characteristic 3 or higher. So we can look at these symmetric polynomials where we don't recognize them. Try to write them in terms of simple characters, we still don't recognize them. So anyways, and of course, we can prove these conjectures in some special cases. We have a pretty good understanding of cohomology if you're close enough to the origin, but this layered structure is just conjectural for weights that are far away from the origin. I think there's a lot of interesting stuff. If we're close to a vertex where there's no overlap between layers, then we can prove again that our prediction is correct, that you get contributions coming from truncated Schur polynomials. And in fact, that also proves that the corresponding truncated Schur polynomials are honest characters because they measure cohomology group, yes. So anyways, I think there's a lot of open questions there. And then, I can ask any number of additional questions. So for instance, I chose the incidence correspondence, lines and hyperplanes, but maybe you can look at lines contained in a 2-plane. That would be another, another partial black variety where you could try to understand cohomology groups. And for that, you would need to not just analyze symmetric powers of omega, but we need to twist it. You need this extra parameter, yes? So this problem is closed only when E is equal to 0. If you start changing E, it gets complicated. Another problem that comes out of our analysis is, when are these truncated Schur functors honest characters, not just alternating sums? Yeah. So, and how do you realize them? How do you write down standard basis for them? Again, we have some ideas for the Schur functors that show up in the incidence correspondence case. It's 2 parts Schur functors, but in general, I think it's wide open. And then there's another conjecture that I think some experts think it's ridiculous, but this is just about the structure of a tensor product of 2 truncated powers. So it turns out we don't know the composition factors. And the conjecture that's, somehow natural from our work is that every composition factor of this tensor product comes from a weight that is p-restricted, meaning when you write it up in terms of the fundamental weights, the coefficients are smaller than p. So if that was true, we would know exactly what the composition factors are, because these p-restricted weights can be seen when you pass to representations of the symmetric group. And for the representations of the symmetric group, this guy is well enough understood. You know, if you restrict to the most generic weight 1, 1, 1, 1, 1, you can see where this comes from. And so, again, there's some interesting combinatorics there. The Moulineux involution would play a role. So if we knew this conjecture, we would also understand exactly the composition factors. And these are somehow the representations that are relevant to us for the incidence correspondence. Anyways, so I'm sure there's many more open problems, but thank you.
All right, are there questions for Claudiu? Yep, Maria.
Yes. So the question is if I'm looking for sure positivity in open problem 2. So I'm looking for positivity with respect to the symmetric functions that describe the simple irreducibles in characteristic P. Yes, so in characteristic P, the simples are smaller than the sure. So you still get a set of symmetric polynomials indexed by dominant weight. And what you want is you want to ask, when is one of these truncated sure functors a positive combination of those? Of course, the big problem is that we don't have formulas like we do for sure functors. And so the question is there another way to just construct naturally some of these truncated sure functors? Yes. Yes. They're not. They're really related. Where is this? I mean, the way we get them is, where is it? Where is it? Here, yes. We understand how to write down these resolutions by exterior powers. I mean, I think this is the crucial. We should know how to resolve sure functors by tensor products of exterior powers somehow. So that's where it comes from, because we can write down those resolutions, and then and then basically compare with the situation. I mean, so Keller, is that correct? That the kind of complexes you get for 2 column partitions are dual to the ones that you get for hooks. So they're not. Anyways, they're related. So they compute the same cohomology. Anyway, I think I mean, that's a fundamental question to understand those resolutions, I think.
Other questions?
Yes. So maybe this exercise, we know how to do it over Z. So I think there's probably still a subtlety if you put Z here, but I haven't thought at all about it. But if you put it as an open problem, if you like, I like linear algebra over a field. So I mean, I think what's important is that everything I defined is really defined over Z, and that allows you to compare things when you pass to different characteristics. Somehow, maybe that's an important thing, to allow yourself to do these constructions, geometric constructions over Z. Because I keep talking about extra cohomology in characteristic P. When you say extra, it means you have a way of comparing. And the reason why there is a comparison is because we can define this over Z and then pass to all those fields, from there. But yeah, I mean, Z is only for those paying attention. Yeah, they really want to.
All right,
Yeah.
question up here.
Yeah, so
Could you repeat the
I mean,
question?
so the question is which collections generate the derived category? And so, yes. So I think what my statement was just about the Picard group, yes? That it's. So I mean, I think even on projective space, you probably want like a sequence like O of 1, O of 2, O of n minus.
You know the quotients,
Yeah. But I mean, I'm saying if generate means you're allowed to twist, then yes.
All right, other questions? Any questions on the chat? No? All right, well, let's thank our speaker again.